All right, before we get started today, we got some class business. At this point, I have 6 students who have not completed exam 1. Now, if you think you've completed it, the best way to find out if I know you've completed it is to go into Brightspace, click on the grades tab, and look for exam 1. If there is no number there, if there is no grade in that place, that means I don't have a grade for you. I have not seen your work. So if you think you've completed the exam but you have no grade, you need to contact me so we can work out any technical problems. Those students who have not completed exam 1 have also not completed any homework. Okay, so what we're doing today is we're looking at chapter 5 of nomenclature. How do we name compounds? And then if we have the name of a compound, how do we write the chemical formula from the name? And that's the entirety of this chapter is on just that topic. All right. So that's a general outline, and I usually don't stop on that one because it's just there for organization purposes. So our model for naming compounds is going to be the binary compound. The binary compound simply has 2 parts to it. Your book may reference that as a binary compound is 2 elements. But it doesn't have to be just elements. We'll find out later that you can have groups of elements bound together so tightly that they behave as a single unit. So I'd rather say the binary has 2 parts. And these compounds can come in basically 2 types. That the one that's referenced there is ionic. And the ionic compounds are those that are composed of a positively charged ion and a negatively charged ion. It's like sodium chloride, right? Table salt, right? It'll have a plus charge on that sodium and a minus charge on that chlorine. That's an example of an ionic compound. There are other compounds, let's see, that are covalently bound. And those compounds form bonds by sharing electrons. We don't have a complete transfer of electrons to one or the other. This is a purely electrostatic attraction that forms the bond. This one is sharing electrons. For instance, water. So we'll have an oxygen and we'll have 2 hydrogens attached to it. And those are not ions. These bonds are shared electrons between the 2. There are naming conventions for the binary ionic compounds and the binary covalent compounds. And we're going to go through them step by step so that you see a logical pattern and an organization that'll make it easier to memorize the rules for naming these compounds. The ionic compounds are always formed between metals and nonmetals. The first one is a metal, the second one is a nonmetal, always. Whereas covalent compounds are always formed between 2 nonmetals. So you'll see that based upon the structure of our periodic table, all those elements to the left of that dark black line are metals, and all the ones to the right are nonmetals. So you're going to find for this type of compound, the metals will come from this side of the chart, and nonmetals from that side of the chart. And we have a name for those. The positively charged ions are cations, and the negatively charged ions are anions. Okay, now let's organize our rules for naming compounds. The type 1 compound is an ionic type compound of a metal and a nonmetal. And the metal is drawn from a part of the table where the metal can only have one possible charge, single charge. So there are only certain parts of the table where that's the case. The first column, the alkali metals, and if you do the extra credits, it'll be easier for you to learn these things. The alkali metals always have a +1 charge for the metal. The alkaline earth, second column, always have a +2 charge. These first 4 here, boron, aluminum, well, we're going to leave boron out because it's a non-metal. So the metal part, aluminum, gallium and indium. Aluminum, gallium, and indium always have a +3 charge. Okay. And there are 3 elements in this transition metal part that have a fixed charge also. I should have used that, single fixed charge. And those are, let me refresh my memory. The periodic table will have that information. Yeah, zinc, cadmium, and silver. So in addition to those that I mentioned, zinc, cadmium, and silver. Zinc 2+ and cadmium, I think it's 2+ also. Yeah. Okay, so these transition metals are fixed charges. And the other fixed charges are the alkaline metals, the alkaline earths, and the boron group. Except we exclude boron because it's a non-metal. So this would be aluminum, gallium, and indium. And they always have a +3 charge. These always have a +2 charge. These always have a +1 charge. Okay, so that's your type 1 compound. And the way we name them is to simply name the metal. For example, let's pick a different one than the one we've used so far. Let's pick calcium. Calcium out of the alkaline earth group. So we write calcium. Well, let's see. Yeah, let's write the compound first. Let's say we're going to form calcium with fluorine. Now, when they're in ionic compounds, the anions, the negative ions, coming from this group, the halogens, are always -1. So that means this fluorine will be a -1 charge, and this will be a +2 charge. And the rule here is that the charges must balance. Compounds are neutral. So if we've got a minus charge, a -1 here and +2 there, we need 2 of these to balance that charge. So how do we name that compound? This would be calcium. And we change the ending for the anion with an IDE on the end. Calcium fluoride. The type 1 compounds are only written this way because the calcium can only have one possible charge. The fluorines only have one possible charge, and all you have to do is balance the charge to write the compound correctly. Type 2 compounds. The type 2 compounds are also ionic with a metal and a nonmetal. But the metals can have a variable charge. Okay. Now, where do they come from? Well, they come from any place metals that we haven't discussed so far. Right. So we've lined these off as fixed charge, fixed charge, fixed charge, and fixed charge here, here, and here for copper, zinc, and silver. The rest of them, all of these transition elements here and all the metals in here that we haven't fixed the charge, have variable charge. So in the compound, they could possibly have 2 or more different charges. Okay, so that means that we still got an ionic compound, but we have to specify in the name what the charge is on that metal ion. So these are going to be transition metals and other, let's see, what's the term they use? Other representative. Metals. The representative elements, that your textbook will probably identify them this way. The representative elements are these 2 columns and everything over here, like that. So the representative elements, that metals are right down here. And you also have a possibility in the actinides and the lanthanides for multiple charge, but we're not going to deal with those to any great extent, so you don't have to worry about those too much. All right, so how do we write these and how do we name these? Well, the anions, let me go further. I talked about the halogens in this column right here, right? These are the noble gases, right? They don't form compounds, typically. The halogens are always -1. Next door to them are the oxygen group, the chalcogens. They're always -2. And next door to those are the pnictogens, the nitrogen group. They're always -3 when they're in a binary ionic compound. So that fixes their charges. So for example, if we form a compound between iron and oxygen, and if you've learned your element symbols so far, you'll know that iron is Fe and oxygen is O. Now, since iron has a multiple charge, right, we don't know what the formula is yet. We have to say what the charge is. So let's for argument's sake, let's say the charge on iron is 3+. And remember, all the chalcogens, the oxygen group, are -2 charge. So how do you balance that? When you have an odd and an even positive negative charge that has to be balanced, cross multiply. So take this 2 over here, take that 3 over here. So 3 times 2 minus is 6 minus, 2 times 3 plus is 6 plus. And together they're 0. So there's our formula for this compound of iron and oxygen. Now, how do we name it? Well, we still say iron, just like before. And we say oxide. But now we have to say, what is the charge on the iron? And to do that, we use parentheses and Roman numerals. 1, 2, 3. That Roman numeral 3 says the charge on iron is 3 pluses. And this way, we can also take that name and write the compound from it. We can take this, say, okay, it's got iron in it, bam. It's got oxygen in it, bam. This has a 3+ charge, write the charge. Oxygen always has 2- charge, write the charge. Then you can deduce the subscripts based upon balancing the charges. Type 2 compounds. All right. So these are some examples. I'm not going to linger here, except to focus on one, hydrogen. When hydrogen is combined with an anion, when hydrogen occupies the metal position, the first position, it's always a +1. But if you have a compound where there's already a metal in there and you attach a hydrogen to it, then the hydrogen occupies the anion position, such as, let me think of a good one. Oh, how about this one? The magnesium hydride. We know that magnesium is a 2+ charge, right? It's fixed, makes it a type 1 compound. And hydrogen would now be a -1 charge. So that means we need 2 of them. So 2 minuses balances the 1, 2+. So MgH2 is magnesium hydride. Okay. So hydrogen can go backwards and forwards. All right. So now we need to look at the last type. These slides are describing everything that I showed you right here. So I'm just going to put them up there so that they'll be recorded. Oh, we got some examples. That's good. It should. We can't use that as an exercise because it's already named. But it does make sense. Potassium is a fixed charge. It's in the first column. An alkali metal, +1 charge. Chlorine is a halogen. It's a -1 charge. So the objective of these naming rules, and all these naming rules were developed and disseminated by a committee of IUPAC. IUPAC stands for International Union of Pure and Applied Chemists. And their objective in these naming conventions, nomenclature, is that the relationship between the formula and the name be unambiguous. Right, so what does that mean? Unambiguous means when you have KCl, potassium chloride is the only possible name. There's no other name that will satisfy and identify that compound. Or if you have the name potassium chloride, the only possible compound that you can write from it is KCl. That's unambiguous. There's no way to confuse it with something else. And then the other rule, this is rule number one. Rule number two is that they're not redundant. In other words, minimal information to convey an unambiguous nomenclature. We haven't run into one that would, we need to get to type 3 compounds, in other words, in order to see the possibility for redundancy. All right, so let's look at type 3 compounds now. Kind of squeezed for room here. Okay, type 3s. Type 3 compounds are covalent. Let's see, there's some other examples. Magnesium bromide, calcium oxide. Calcium is a 2+, oxygen is a -2, so you only need one of each. Oh, here's an exercise. Okay, we can do this. Name the compound SRBr2. SRBr2. So what is SR? Right, that was one of those elements that I had you memorize. SR is strontium. So we write strontium and bromide. Okay, the question is it, since strontium is a metal, bromide's a non-metal, then it's either a 1 or a 2. So which one is it? Well, we look for strontium. Where is it located? Strontium is located in the second column, the alkaline earths. That means it has a +2 charge. Right? And you can deduce this also from here. If this is the correct compound, we know that bromine's a -1, so this one has to be a +2 because there are 2 of them. But we also know that strontium comes from the second column, which makes it a type 1 compound. This is a fixed charge. Strontium will not have any other possible charge. So strontium bromide is the proper name. We could possibly see redundancy here, right? If you write this that way, it's correct. It's unambiguous and not redundant. But if you get confused about type 1 and type 2 compounds and you say, I better put this in here, that's redundant. You don't need it because strontium can only be a +2 charge. And that would be a wrong answer. All right. Strontium bromide. Okay. We're still looking at type 1s and type 2s here. Okay, hold on type 3s for a second. Notice where iron comes from the transition metals, and it's not one of these fixed charges. There, see, there, and there. Copper, zinc, or silver. And chlorine is a halogen, so it's always a -1. So if we write this compound, we have to specify the charge on iron. Now, we can't do that yet because we haven't been given a formula. We don't know what the charge on iron is. See, iron could be a 3+ or a 2+. And we would name it this way, here, here, here. Copper could be a 2+ or a 1+. Let me see. Is that true? They say it's true. Yes. That was my mistake. Copper can have more than one charge. The fixed charges are zinc, cadmium, and silver. I correct myself. Zinc, cadmium, silver have fixed charges. Copper does not. Cobalt can have 2 charges. Tin can have a couple of charges. Lead can have a couple. Mercury can have 2 charges, but notice that that's a 2+ and that's a 2+. So why is that? Right? It's a funny thing about mercury. Mercury with a 2+ charge is simply written as a single atom. But if mercury has a 1+ charge, it's always written like this. Right? So that means you have 2 mercuries together, bound together, and overall they have a 2+ charge. But each one of the mercuries has a 1+ charge. Don't ask me why, it just is. Okay, another thing I'll point out on this chart is they've included legacy naming on the right-hand side. And the old way to name these metals was ferric, ferrous. Ferrous is the 2+, ferric is the 3+. Cuprous is the 1+, cupric is the 2+. So see where the problem arises? If we end the name with us, if it's copper, it's 1, but if it's iron, it's 2. That can lead to confusion. So the newer naming system that was adopted back in I think it was the 70s sometime, went this route, where you simply say, what is the charge on the atom, on the metal? And then we leave these behind. You may still see those occasionally on old bottles of chemicals or in the popular literature or even on some items that you buy at the grocery store. Right? So if you buy toothpaste and it's got fluorine in it, right? Fluoridated toothpaste, it may say you have on the label of the bottle, it may say stannous fluoride. Right? That's what we call a trivial name. So stannous would be tin with a 2+ charge. This would be the proper name. This would be the trivial name. All right. So we did one of these already with iron. Here's an example. Copper 1 bromide. How do we know to put a Roman numeral there? We find it on the periodic table, and it's not one of the fixed charges. And your periodic table will also give you charges, right? And you can use the periodic table when you take an exam. Well, you can for the second exam. For the first exam, you won't need it. But for the second exam, you can use the periodic table that's located in useful information in Brightspace in the same module where you find the link to the exam. There's also a useful information document there that you want to print. Because once you go into Brightspace lockdown browser and Respondus Monitor, it will lock you out of everything else. So you need to have that printed out beforehand, and it's okay to use anything that's in there with the exam. That information is valid. You can use it during the exam. If you use the review documents that are also in Brightspace for review purposes, Then you'll also find, this is the one for exam 2. It looks like an exam. But at the very back, there are pages with useful information. Like there, and periodic table. And all of that information is duplicated in the Brightspace module where you find the exam. So if it's on the review document, you will have access to it for the exam. So there's one example. Let's see, I'm sure they've got another one. So how do we know that it's iron 2? If we write it like that, well, sulfur is in the same group as oxygen. It's a chalcogen, which means it has a -2 charge. Right? That means with only 1 and 1, this one has to be 2+. It can't be anything else. So that's why we name the compound iron 2 sulfide. By the same way, we find that this oxygen is a 2- charge, but 2 of them makes a -4 that has to be balanced by that one lead. That means that one lead atom must be a +4 charge. And that dictates this part of the name. All right, we're going to do another one. What's the name of CrO2? Okay. Well, we know that oxygen has a 2- charge, so that means it has a 4- total. So this one has to be a +4. So we know the charge. Now we need to name it. What is Cr? Well, you've got that memorized already. You should write chromium. Plus, you look and you know where chromium's located. Right? Chromium is a transition metal. It has the potential for multiple charges. That means we have to say the charge on chromium and then finish it off with the anion. Chromium 4 oxide is the proper name for this compound. Okay. All right. Let's see, we'll be getting close to type 3 compounds in a second. Oh, we got another detective story here. What's the correct name of the compound that results from the most stable ion of sulfur? The most stable ion of sulfur is what? We know that sulfur is a chalcogen. It has to be a 2-. And the metal ion that contains 24 electrons. So we've got a metal here, and we know it has 24 electrons. Right? So what must the charge? Now, to solve this problem, we have to assume that there's 1 sulfur and 1 metal. If we don't do that, then we can't solve the problem. So if we assume it's 1 here and 1 there, now we can work with it. The charge on this one then would have to be a 2+. So if it has 24 electrons, but it has a 2+ charge, how did it get that charge? We covered that in chapter 4. It got that charge because it has an excess of 2 positives. Where do the positives come in an atom? They come from the protons. So that means it has to have 26 protons to give you an excess of 2. Now we can identify that element. 26 protons, look on the periodic table. 26 is iron. Right? And we know it's 1 and 1. So now, name the compound. Iron 2 sulfide. There we go. Now we're back. We finally made it to type 3 compounds. They are covalent compounds, which means it's a non-metal and a non-metal. Now, why is it a non-metal non-metal to make a covalent compound? Well, when you have a metal and a non-metal, the metals tend to want to give up electrons, and the non-metals tend to want to receive electrons. They have a draw for electrons, whereas a metal wants to give them up. So you're more likely to form an ionic compound between a metal and a non-metal. But when you've got two non-metals, they both want those electrons. So the only way they can satisfy and bond is to share. So these non-metals share their electrons. Here's the problem. Our naming convention up to this point has been metal, non-metal, which means cation, anion. But these do not have charges. Since they don't have charges, we can't work with balancing charges to determine how many of each one is in the compound. But we're going to borrow from the type 1, type 2 compounds and put one of them first and one of them second. The first element is nearly always, if you have two elements, non-metals, the first element in the name is nearly always the one to the left or below, left and below, because it's closer to the metals. And that being the case, we simply name it as if it were a metal. Just write the name of the element. And then the second element, we write with the IDE ending. Okay? But in order to name them, since they don't have charges, we can't designate a charge with a Roman numeral, right? So we have to use an alternate method. We have to learn the Greek prefixes for numbers of things. So mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. We use those prefixes to say how many of each element is in that unit. All right. This list only goes down to 8, but I gave you 9 and 10. 9 and 10. Nona is 9 and deca is 10. Okay, so let's get an example here. Carbon and oxygen are both nonmetals. You know where they come from, the right-hand side of the table to the right of that black line. Carbon and oxygen are both nonmetals. That means if we have a compound and we have to be given the formula, we cannot deduce the formula. Carbon dioxide is like this. We say carbon because it's first, and oxide because it's second, and then we have to say there are two of them. Notice we don't say monocarbon dioxide. By convention, if you've got carbon written there, it has to be at least one of them. So we don't say monocarbon dioxide. Strangely enough, if we have a single on this side in the second position, we do say mono. Let's see if they got an example for that one. Not yet. Sulfur hexafluoride. Hexa is 6. Now, if you have more than one, you will say dinitrogen in this case. Dinitrogen tetraoxide. Notice we dropped the A off of tetra. It just sounds better. Right? Instead of saying tetraoxide, we just say tetroxide. Let's see. Let me think of one. How about this one? N2O. The old way of naming that is nitrous oxide. Right? If you've been to the dentist and they've put gas on your face, then you breathe this stuff in. Nitrous oxide. That's the trivial name. That's the old way to name it. The current way to name it is dinitrogen monoxide. Okay, so there's only one of them here. So in this case, we do say monoxide. Dinitrogen oxide, you would think it's logically correct, but the committee, the IUPAC committee said, no, if it comes second, we're going to say mono. All right. What's the name of this compound? Well, first of all, we have to find out where those elements come from. We know oxygen's a nonmetal. How about selenium? Selenium sounds like a metal, doesn't it? So we use our periodic table. And we find selenium is in the same family as oxygen, and it's to the right of that black line. So these are both nonmetals. That means we use the convention where we say selenium dioxide. And that is both unambiguous and non-redundant. We don't say 2 or 4 in this case because selenium's not a metal. Okay. That would be wrong. We're using the type 2 convention for a type 3 compound. All right. So how do we decide? Right? This is a decision tree. You have a binary compound and you look at it and say, okay, is there a metal in that first position? If yes, there's a metal, then you're either 1 or 2. Right? If you're 1 or 2, then you have to decide, does that metal possess the possibility for multiple charges, or is it fixed charge? If it's a fixed charge, you go to type 1. If it's a multiple charge, you go to type 2. And if it happens to be a nonmetal and a nonmetal, you'll automatically go to 3. So that's your decision process for naming compounds. Now, here's a fly in the ointment. I'm going to have to erase this to make room for the rest of it. I'll leave as much as I can up here. There we go. So for this one, you use Greek prefixes. Okay. The problem here is polyatomic ions. I alluded to them early on. Polyatomic ions are just what it says. There's more than one atom together, bound tightly together, so that they behave as a single unit ion. The charge on that ion is spread over the entire group. And each one has its own special name. This is not strictly speaking true. You don't have to memorize them, because in your review document and in useful information available for the exam, there's a chart right here. Common polyatomic ions. On one side, you got the name and the ion formula sorted by the name in alphabetical order. And on the other side, you have exactly the same ones here, only this side is sorted according to the formula. Now, if you work a lot of those problems, and if you use the resources that I've made available to the class in Brightspace, then you'll get so much practice that some of them you'll just automatically remember. You'll memorize them without realizing. Here are some common ones that are presented in your textbook. Actually, this is the 7th edition. I think we're already up to what, 9th or 10th edition by now. But these are presented in your book, and my list is more comprehensive. Notice that in this list and in my list, all of the polyatomic ions are negatives, except for one. This one right here. Ammonium is a positive. It's a cation. That means that is the only one that can occupy the first position in a formula. The rest of them have to come in the second position. Okay. So once you know that you have a polyatomic ion, then you know that this group is going to be named with that name and no other. Let's get some examples. I think it'll work better. Well, some do form logical groups. Maybe this is a good time to cover that. Notice that all of these, and many of them, are combinations of nonmetals and oxygen. So here we have oxygen, oxygen, there's oxygen all the way down here. Oxygen, oxygen all the way through here. Well, there's an oxygen. There's no oxygen here, but there's an oxygen here, here, and here. Okay. So that can help you identify polyatomic ions in a formula that's given to you. If you have 3 or more atoms in or elements in a formula, and one of them is oxygen, then you may want to think about, maybe I got a polyatomic in there. So this logical group, I start with chlorine and oxygen O3 minus, chlorate. So if we say ClO3 minus, that name is chlorate. If we take away one of the oxygens, and they're going backwards, I'm going down this way. We take away one of the oxygens, this is chlorite. Now, these naming conventions for polyatomic ions are sort of grandfathered in. I think the IUPAC committee couldn't come up with a substitute, a better way of naming them, and everybody was using these names already. So they just dovetailed it into the system. If we take away another one, like that, now we don't have any more suffixes that we can tack on the end that will progress down. So we add a prefix and we say less than or underneath the chloride. That's hypo. Okay. Hypo is the Greek prefix that means underneath. That's why when you get a shot, they use a hypodermic needle, one underneath the skin. It goes underneath the skin, hypodermic. Then we can go one more the other direction. Right? So we need another prefix. And the prefix for this one is per. That means above. So greater than chloride. So we just add another oxygen and get per. There are several that work like this. This one, the nice thing about this is these polyatomics, if we substitute a different halogen in that position from this family, then the naming conventions are the same. So what if I substitute a bromine in here? It's a halogen, just like chlorine. So in this case, we would say let me erase this part. So this would be, this one would be bromate. This one would be bromite. This would be hypobromite. Oops. Bromite. And this would be perbromite. Perbromate, excuse me. Bromate, bromite, hypobromite, and perbromate. And you can do that also with iodine. It's in the same family. So it'd be iodate, iodite, hypoiodite, and periodate. So with that sequence, once you learn that sequence, that gives you 12 polyatomic ions right there. You can recall them instantly. And there are a couple of other situations in there like that, not as extensive as this one. For instance, NO3 minus is nitrate, and NO2 minus is nitrite. Okay. That's the only two in that group. Let's see. How about this one? SO4 2 minus. That's sulfate. If we add a hydrogen to that, in this case, the charge does change. Because remember, the hydrogen on the front has a +1 charge. So a +1 is going to neutralize one of those negatives. And this one now is hydrogen sulfate. Okay. But we can also change this to a 3. Now this is sulfite and hydrogen sulfite. So there is sort of a logic to it. All right, there's the complete list in microtype. All right. So examples of naming. In this case, we have that cation, that's the only cation in there, and we're going to pair it with another polyatomic. That's legal. So for that one, we know that NH4 is ammonium. Right? And the second part is a polyatomic called acetate. Ammonium acetate. In this case, this charge is fixed. This charge is fixed. This is a +1 charge, this is a -1 charge. That being the case, since the charges are fixed, we treat them like a type 1 compound and just say the name for this polyatomic ion, the name for that one, ammonium acetate, that's it. That is unambiguous and non-redundant. All right. How we doing on time? 10. Still got an hour, I think. Yeah. All right, some more examples. Notice we've got a metal here, and we don't have a single element here. So that's kind of a giveaway. This is a polyatomic ion. The polyatomic ion here is called hydroxide. And hydroxide has a -1 charge. Sodium has a +1 charge. Right? So we treat it like a type 1 compound and call it sodium hydroxide. That's it. We don't have to say how many there are. Now, what do you do if the formula calls for more than one polyatomic in the formula itself? Well, the rule is that these polyatomics cannot be broken up. You cannot change the subscript. That polyatomic is fixed. NO3 is sacred, cannot be touched. It's a -1 charge. Magnesium is an alkaline earth, second column, +2 charge. That means it's a type 1 compound. So we have magnesium and then nitrate. We don't have to say how many there are, but we do know that with magnesium as a 2+ charge and nitrate as a 1- charge, we need 2 minuses to balance that 2+. But we cannot change the subscripts. Remember, the negative charge is spread over the entire molecule. So if you change the subscripts, you've changed the polyatomic. And you don't know what the charge is then. So we have to use parentheses. And there are 2 of them. That also is a giveaway. If you see a formula with a group of elements together and a parentheses around them with a subscript, you know that's a polyatomic. Here's one where the polyatomic is the first member, the ammonium. So we say ammonium sulfate. Sulfate is a 2- charge. Ammonium is a 1+ charge. So we have to have 2 ammoniums to balance that 1 sulfate. And we use the type 1 naming convention because the charges are fixed. Now in this case, we have a metal and a polyatomic. Now you have to ask yourself, where does that metal come from? Is it a fixed charge or is it a variable charge? In this case, we know that iron is a variable charge, which means with this formula, we have to balance charges, iron and phosphate. Well, the formula says there's only 1 of each. We look at our table, we find that phosphate is a 3- charge. That means iron has to be a 3+. That's the only possibility. Now, when we write the name, we have to use the type 2 convention. And the Roman numerals tell us the charge on the iron. Okay, so here's another decision tree. Binary compound. Is it a polyatomic? Is there a polyatomic ion there? Well, okay. What they're naming binary is 1 element, 1 element. The way I described it is 1 form and another form. One possible. You broaden the definition of element to include polyatomics. Right? So this is really not necessary for our purposes. right? Because we have taken the definition of binary one step further to include polyatomics already. So I probably ought to get rid of that slide. So what's the name of this compound? KClO3. Well, we've got 3 elements in here, right? And one of them is oxygen. So we should suspect polyatomic. Well, this is not a polyatomic. This has to be the polyatomic. So we look it up, and it happens to be chlorate. We know it's a -1 charge because potassium is a +1 charge. It's an alkali metal. First column, always +1. So we know that we can write potassium, and we don't have to say the charge at all. It's a type 1. But now we need what's the name of that? And it turns out it's chlorate. So potassium chlorate is an unambiguous and non-redundant name for that formula. All right. I'll get another one. All right. Examine the following table of formulas and names. Which of the compounds are named correctly? Okay. Let's figure this one out. First one, P2O5. Is it named correctly? Well, it's a non-metal. So we're using a type 3 convention. So we have to say 2 phosphoruses, diphosphorus, pentoxide. Okay, that one's correct. But the next one, ClO2. ClO2. Notice this is a compound. This is not a polyatomic because there's no charge, right? This is a neutral compound. So what is it? A non-metal and a non-metal. Type 3 again. And so we say chlorine, there's only one of them. Dioxide. That one's wrong. Right? Theirs is wrong. How about PbI2? PbI4. PbI4. What type of compound is this? Well, it's a metal and a non-metal, so it's a 1 or a 2. And then the lead comes from transition metals. That area of the transitions where, actually it's not a transition, I'm sorry. It's a representative element, but it's not a non-metal. It's over to the far right underneath the stair-step black line. But it has the possibility of multiple charges, so it's a type 2 compound. We have to say lead, what's the charge? Well, iodine is a halogen, it's always -1, so that means this one has to be a +4. Iodide. Okay, that one is, theirs is wrong. How about this one? CuSO4. All right, copper. Copper is one of those that has multiple charge. One of those metals, so it's a type 2 compound. So we have to say copper. Now we need the charge. What's the charge? Well, the polyatomic here is a 2-. So this one has to be a 2+. And this is a polyatomic that we name sulfate. Copper 2 sulfate. No, that was wrong too. The only correct one is the first one. Right there. Okay. Now, thought we were finished, huh? No. We've got to learn how to name acids. So if we're going to name an acid, how do we know we have an acid? Right? That's a trick. Well, by convention, acids always start with at least one hydrogen, sometimes more. And if they have hydrogens in the rest of the molecule, they're not at the beginning, they're later. So you can have hydrogens, more than one hydrogen separated, but the first hydrogens are what we call the acidic hydrogens. Now, you recognize them by the first hydrogen in the molecule, like this one, or like this one with a polyatomic, or like this one with another polyatomic. Okay, those are acids, but they're only acids if they're dissolved in water. They have to be aqueous. Right? If HCl is pure, a pure substance, not dissolved in water, it's not a mixture. If we wrote it like this, it would be a gas. And in that case, we would call it hydrogen chloride. Okay. But if it's like this, what do we call that? Well, we have some rules. The first one has to do with, after you've identified the hydrogen, is there oxygen? Is there oxygen in the other part of the molecule here? Yeah, there's the oxygen, there's oxygen. This has no oxygen. If there's no oxygen and it's an acid, it's dissolved in water, then we start the name with hydro. Right. Now we're naming the acid. We started with hydro, then we take this part of the molecule, the chloride, and we change this ending to ic, IC. I to become X. So this is hydrochloric acid. Okay? That's only if there is no oxygen. And let's see, examples, hydrochloric acid. Right? There's another polyatomic, cyanide. So if it were a gas, it would be hydrogen cyanide. But if we dissolve it in water, now it becomes, since there's no oxygen, so we start the name with hydro. And then cyanide becomes ic, cyanic acid. All right. See, this is starting to get a little weak. Try another one. How about this one? H2S. If we have H2S, hydrogen sulfide, anybody who's been close to White Sulphur Springs or Green Sulphur Springs or any of those Greenbrier County places will smell hydrogen sulfide. Or if you get close to a paper mill, they use sulfuric acid and it generates these gases. And one of them is hydrogen sulfide. But if you dissolve it in water now, aqueous, there's no oxygen, so we started with hydro. And then rather than saying hydrosulfic, just doesn't sound right, we extend the name to sulfur and we say sulfuric acid. So hydrosulfuric acid is H2S. Whereas this one would be hydrogen, dihydrogen sulfate, would be, well, let's see, we haven't got that rule yet. Let's get the rule first. There are other examples of acids that have no oxygen in the molecule. Now, if they have oxygen, you don't start with hydro. You go to this part of the name, right? This is the sulfate polyatomic ion. And this name, this part of the acid naming convention will always be referencing polyatomic ions because they're the only ones that have oxygen in them, along with the hydrogen. So 8s become X. So instead of saying hydro, we just say sulfuric acid. Okay, that's it. Or nitrate is the polyatomic part of this acid. 8 becomes ic, so it's nitric. What if it's HNO2? Right, that's possible. Right, that's a -1. This is a -1 with a plus hydrogen. Right, this is nitrite. This polyatomic is nitrite, not nitrate. Nitrites become us. So this would be, that's aqueous, nitrous acid. Okay. What if we had this one here instead of that? We'd have SO3. SO3 is sulfite. So in that case, it would be sulfurous acid. Oh, there's a good one. Let's remove these, make room. If we make an acid out of the acetate, C2H3O2 is a minus. That's the acetate polyatomic ion. If we add a hydrogen to it, right? Now the molecule is neutral. And we put it in water. Okay? That's got an oxygen in it. So we don't start with hydro. We just say, this is acetate, 8's become X. So we say acetic acid. Acetic acid, 5% acetic acid is vinegar. You can also, in fact, when I was in research, we would often buy 100% hydrogen acetate, but we still called it acetic acid. It was labeled that way, even though there was no water in it. 100% is also called glacial. Glacial acetic acid is 100%. And we'll talk about acidity later, I think, in terms of strength. Like these are strong acids. That's a strong acid. This is a, I'll erase the others. This is a weak acid. But if you get 100% acetic acid, glacial acetic acid, it may be a weak acid, but it can still eat your hand because it's so concentrated. All right. And there's the one with us in it. Nitrous acid, sulfurous acid, chlorous acid, right? Remember, this is chlorite. That's chlorous acid. And remember, all of these have to be in aqueous solution. All right. Common oxygen-containing acids. So there's your decision tree. Does it contain oxygen? Well, first of all, before you get there, you got to ask yourself, is it an acid? Right? First of all, does it have hydrogen as the first element in the compound name, compound formula? And is it in aqueous solution? And then you ask yourself, is there oxygen? Then you go to one or the other. So we're going to see if we can catch them misnaming acids, just like we did for compounds earlier. All right. Oh, wait a minute. Which of the following compounds naming acids? Well, okay. We're dovetailing in previous. Only one of these is an acid, right? No hydrogen there. Right there. That's an acid. Yeah. So let's go ahead and name the rest of them. Is this first one correct? KNO3. Well, it's potassium. And potassium is a type 1 because it's fixed charge. It's in the first column. Potassium nitrate. Yep, that was good. TiO2. Titanium. And then we have oxide. Titanium is a transition metal. And it's one of those with variable charge. So if it's got two oxygens, that means we have to balance a -4 with a +4. Right? That one's wrong. Theirs is wrong, mine's right. How about this one? SNOH4. Okay, SN is 10. And OH is a polyatomic ion. Is hydroxide with a -1 charge. So we got 4 of them. That means we have to balance this one with a +4. So we need there 10,4 hydroxide. That one's correct. How about this one? I think writing the thing up here, writing the formula up here is a good idea. I should have done it on that one. Okay. Here we have 2 nonmetals, type 3 compound. There's only 1 phosphorus. OUS or US is correct, either one. This is the way the English write it. And on this side of the pond, we write it without the O. Usually. Okay. And then we have 5 bromides. Pentabromide. Yeah, that's right. And the last one, H2SO3. We named this one already, didn't we? This one has oxygen, so we don't start it with hydro. So we look at this part, which is sulfite. Ite becomes us. So we say sulfurous acid. So that one is incorrect. Wait a minute. Yeah, oh yeah, these are all correct. The only one that's incorrect was, okay, we'll go to the next slide, sorry. Sodium hydroxide. This is a base, counterpart to the acid. That's what you put together when you want to neutralize an acid, you put a base in there with it. But the bases don't need special naming conventions. You just name them like we would before. The cation position followed by the anion position, which will always be a hydroxide. Potassium carbonate. Potassium is a fixed charge, +1. Carbonate is a polyatomic ion with a 2- charge. So to balance the charges, we need 2 potassiums. Sulfuric acid, we did that one before. I'm not going to beat that one again. Dinitrogen pentoxide. We know it has nitrogen, it has oxygen, and correctly, Greek prefixes tell us how many because these are both nonmetals. It's a type 3 compound. Cobalt, yes. Cobalt is one of those that can variable charge. We're given that the cobalt has a 3+ charge. Oops, is that right? Little o. Cobalt has a 3+ charge, and nitrate has a 1- minus charge. So how are we going to get 3 minuses out of this? That's a polyatomic. You have to use parentheses. There. So we need big C, little o, and NO3 taken 3 times. All right, got a detective story here. See if we can figure this one out. A compound has a formula XCl3, XCl3, where X could represent a metal or a nonmetal. Ooh, it could be an M or an N, metal or nonmetal. What could the name of this compound be? Is that all the information they're giving us? Let me flip over my hard copy. Okay. Oh, we're given, sorry. This is multiple choice. There we go. Which one of these would be valid? Well, if it's metal or non-metal, there's a non-metal, non-metal, metal, metal. Okay. Could it be phosphorus trichloride? Right? Phosphorus trichloride. Yeah, it could be that one. Right? Metal, non-metal. We just say how many there are based upon that formula. So X is P, that's good. How about carbon monochloride? CCl3. Well, that means no, because there are 3 chlorides. We can't say mono, we have to say 3. Right? So that was wrong. How about 10, 4 chloride? Well, 10 would be a +4 charge. Chloride's always -1, there'd be 4 of them, right? So no, can't be that one. How about magnesium chloride? Right, so magnesium has a 2+ charge. It's an alkaline earth, always 2+ charge. And chlorine is a -1 charge, so we need 2 of those. Right? No, can't be that one. So the only one it can be is this one, out of those that we're given. Okay. This last slide I threw in there myself, because there's one other naming convention that wasn't covered in your book. And it has to do with hydrated compounds. Waters of hydration. Sometimes if you look on the chemical jar, or sometimes on in the drugstore, especially, let's see, which one would it be? Epsom salt would be a candidate. When you have a hydrated compound, the compound name sits here, and then it's attached to so many waters. Right? So you have the name of the compound here, the formula of the compound, and then a dot in the middle of the line, and then a number of how many water molecules are attached. These are independent, separate water molecules, but they're in the crystal structure of the ionic compound, right? So these are always type 1s or type 2 compounds will have the possibility of this. Now, what is a water of hydration? Well, aside from being this naming structure, this formula structure, waters of hydration are those water molecules that are still in the crystal matrix after we've heated the compound up to 105 degrees Celsius. 105 degrees Celsius will evaporate most of the water of a wet compound. But beyond that, it still hangs on to some of those waters. And at that point, those waters are considered part of the molecular structure. You have to heat them up higher, like 150 degrees, 160 degrees Celsius in order to drive off those other waters. Sometimes we heat them higher than that. Okay. So if we know that the water molecules are part of the structure of the compound, how do we name it? Here's an example. This is zinc sulfate. Right? And zinc is one of those that is a fixed charge. It's always 2+. And this polyatomic is always 2-. So we name it like a type 1 compound. And we would name it zinc sulfate. Okay. That's the name for that formula. But sometimes compounds have waters attached to them, and in this case, this compound, and these can vary also, right? Waters of hydration can be a certain amount, and then that same compound could have more, and they're considered a different compound. So in this case, we've got 7 waters. Let's get rid of those. We don't need those. 7 water molecules for every 1 formula unit of zinc sulfate. The ratio is 7 of these to 1 of these, right? There's a 1 out here, 1. So when we do that, we say how many waters are attached to this formula by prefix, excuse me, not septa, hepta. Hepta hydrate. Hydrate is an old word, and it's derived from the parts, the prefixes, suffixes. That means hydra refers to hydrogen, like hydrogen, and ate is an ending that refers to oxygen. So hydrate is water. Zinc sulfate heptahydrate is that compound. Okay. There's an extra credit in Brightspace that's available for naming compounds. This will be a good time to start using it. And there are a couple in there that have waters of hydration. That's another reason I wanted to give this slide, so that when you come to that point, you'll know how to name the compound. All right, I think this is our last slide for today. Yep, that's it.